In the world of unsupervised learning, we often face a unique challenge. How do we know if our clustering algorithm actually did a good job? Since we don't have predefined labels to check against, we need a mathematical way to measure the fitness of our groups. This is where the silhouette score becomes an essential tool. It provides a quantitative measure of how well each data point fits within its assigned cluster. At its core, the score evaluates two competing forces: how tightly the points are packed together inside a group, and how well separated those groups are from one another. By looking at these two factors, we can determine if our clusters represent genuine patterns or just random noise. To understand the math, we first need to define two specific values for every single data point in our set. The first value is called A, which represents cohesion. We calculate A by finding the average distance between a specific point and every other point within that same cluster. If A is a small number, it means our point is very close to its neighbours, indicating a dense, well-formed cluster. The second value is B, which represents separation. To find B, we look at the average distance between our point and all the points in the next nearest cluster, the one it wasn't assigned to. Ideally, we want B to be a large number, signifying that our point is far away from any other potential groups. Now we combine these two values into a single formula. The silhouette score for an individual point is calculated as B minus A, divided by the maximum of A or B. By dividing by the larger of the two values, we normalise the result, ensuring the final score always falls between -1 and +1. This normalisation allows us to compare the quality of clusters across different data sets, regardless of the actual distance scales involved. Think of this calculation as a way of asking, how much more do I belong to my current group than I do to my closest neighbour? If B is much larger than A, the numerator will be positive and the result will climb toward 1. Interpreting the final results is straightforward, but reveals a lot about our model's performance. A score near +1 is the gold standard. It tells us the point is very far from neighbouring clusters and sits comfortably near the centre of its own group. A score near 0 is a sign of trouble. It suggests the point lies right on the decision boundary between two clusters, making its assignment somewhat arbitrary. The most critical result, however, is a negative score. If the score is closer to -1, it means A is actually larger than B. In plain English, this means the point is closer to a different cluster than the one it was placed in, suggesting a likely error in the clustering process. By averaging these scores across the entire dataset, we get a global silhouette score that tells us if we've found the optimal number of clusters for our data.